Hello everyone. So we talked about the capillary pressure in reservoir, and we mentioned that most of the reservoirs are water wet. So if we want to define the capillary pressure, then the capillary pressure is equal to the pressure of oil minus the pressure of water. And from what we had in the previous slides, the equation for capillary pressure was the density difference of oil and water multiplied by H divided by 144 if we have these two phases present, right? So if I write the equation here, multiplied by the height of the water in the capillary divided by 144, and if you look at this equation, you see this is a positive number, and the density of the water is more than the density of the oil, so this is a positive number. So overall, this number is a positive number, right? So that means that the pressure of the oil should be higher than the pressure of the water, right? So the pressure of non-bedding phase is greater than the pressure of the bedding phase. All right, so now let's continue, and we want to talk about what implication it has in terms of reservoir engineering. So you can consider, to make it a simple case, you can consider the rock as a bundle of capillary tubes. We did this example with when we were defining the permeability, right? So let's consider that you have a bundle of capillary tubes, and if you don't have any capillary tube and just you have a bucket, and then you pour water here, and then you have oil on the top. You remember we discussed this: the oil will go on the top, the water will be at the bottom. The boundary is pretty smooth and horizontal, and then there is no capillary pressure here, right? Now if you put some capillary tubes into this bucket, then what happens with different radiuses? Well, the water starts to go up, right? And in different capillaries with different cross-sectional areas, the height at which the water will go up would be different according to the definition of capillary pressure, right? So the one PC was equal to 2 sigma cosine theta over R, right? And if you consider one capillary tube and two different fluids, then this is also equal to the density difference between two phases. So rho W minus rho oil multiplied by the height divided by 144, right? Okay, so we had this equation. So the height at which the water goes up depends on, inversely, is proportional to the radius of the capillary tube, right? So the larger the capillary tube radius, the lower would be the height of the fluid, in this case water, inside the capillary tube, right? So if I have a larger tube, I will have water going up through the capillary tube less, right? Now the question is, how much does this water go up? Remember we talked about this, it depends on how much is the weight of the fluid or gravitational force that is applied, and it's always a competition between the net adhesion force and the weight of the fluid inside the capillary. Anyway, so if you have a bundle of capillary tubes, which we assume that our rocks are like that, and you remember we talked about that the water we have in the reservoirs, we have water, oil, and gas. If you have a bundle of capillary tube, you will see that you will have different heights of the water in different capillaries, right? So that's the same in porous media actually. In porous media, you have pores with different radiuses, right? And if you have a water wet system, then the amount of the water in smaller pores will be more than the pores that are larger in diameter. Okay, now consider that you have a vertical reservoir. At the bottom you have water, right? And then the water will rise through these small pores with different proportionality, right? The smaller the pore radius, the higher the height of the water in those pores. So if you have a water wet tube, which we did an example on that, right? Water tries to wet the surface. The contact angle would be close to 0, and since the contact angle is close to 0, then 2 sigma cosine theta over R This is almost 1, and this is a positive number, this is a positive number, so your capillary pressure is positive. Therefore, the pressure of the oil is greater than the pressure of water, because capillary pressure is defined as PO minus PW, right? So this is what we are talking about here. And the implication is that if you want to displace water from that tube, you need to inject, you need to put some force to the oil to be able to displace water out of the capillary tube. Okay, so however, if the pressure of the oil is reduced, the water will displace the oil automatically or spontaneously, which causes the production. The reason is that the water always tries to wet the surface, right? The net adhesion force, right? Now, when does it stop? If the pressure of the oil is not enough, the water will displace the oil completely. Okay, so in the reservoir engineering, we have racks with different pore sizes. We just mentioned that, right? And in those reservoirs, the fluid, which is the water, usually at the bottom of the reservoir, and we have pores with different radiuses. The water again advances to those pores for different heights. You see the lowest radius capillary have the highest height of water inside it. And if you draw the pressure as a function of height for each phase, okay, remember pressure can be calculated by rho gh, right? That's how we calculate the pressure. So pressure versus height is a line, and in this case h is equal to pressure over rho g, right? So it's a linear line with the slope 1 over rho g, right? So for the case of the oil, this is going to be 1 over rho g, rho oil, multiplied by pressure of oil. In the case of the water, it's going to be 1 over rho w g, multiplied by pressure of water, right? So we know that the density of the water is higher than the density of the oil. Therefore, this slope is going to be lower for the case of the water, because density of the water is higher, right? So if you look at the pressure as a function of the height, or height as a function of pressure, you can see that this is the water line, this is the oil line. This is how the pressure of the oil is changing. Okay, now the intersection of these two lines is called free water level, and at that point means that the pressure of both phases are equal to each other. So pressure of water is equal to pressure of oil, which means that your capillary pressure is equal to 0 at that point. And which point is that? Let's look at. It's the free surface, right? Free water surface. So this is called free water level, and we use this language in petroleum engineering as well. Okay, so free water level is the level at which the capillary pressure is 0. You have 100% water at that level. You have 100% water at that depth. Okay, so if you look at all the locations inside your reservoir at that point, there is 100% water. You cannot find any oil at that depth. Okay, there are some more definitions which we will go over them in future slides, but we'll stop here, and in the next video we will continue on this topic.